Good morning, everyone. Let's get started here. If you are watching online, make sure that you turn on your cameras. Um, so today, we will finally be able to finish the management zone creation exercise. Last class, we were working on just validating them, understanding what they were. So right now, my environment is empty. So I will have to basically rerun. All right. Basically rerun some chunks. And if that's the same for you, make sure you follow along with me. So beginning at the top of the script, we're just gonna load all the packages.
So on one line, like the computer that I'm using doesn't have the camera.
Oh, no worries, no worries. I mean, you're here. I can see it. Yeah. Yeah, so please go ahead and run the chunk for the packages. We want to import the OLV data set, so also loading that chunk, bringing in the boundary, so run that. We don't have to run the summary. We don't have to run any of the k-means explanation chunks. The next one you have to run is the OLVN. So make sure you run that. We don't have to run this first mod KM because we were just exploring k-means in itself with our data. You do not need to run any of the finding k chunks as we have already ran them and decided to go with 2 clusters. You do have to run mod km2 chunk. So we have this object since that is our final k-means model that we decided to move forward. Make sure you also run the zone df chunk so you create that object. And then here we have that map of the unsmooth zones. I guess we really don't have to run that. I mean, you should have already exported this map here, which you will use during the assignment. So if you have not exported that, you can run that now, but we already went through that in class, so maybe you don't have to. Then we talked about the focal filters or smoothing zones using a focal window. So go ahead and run the grid R chunk as well. So we have a grid there. And then the following chunk, which is where we actually did the smoothing using a matrix of size 5 by 5 and using a function mean. So make sure you run all that chunk as well. And then we don't have to run this again, but if you don't have this figure, you should, because we will be using this for the assignment as well. And then make sure you have the zone SDF chunk run. I believe that's the object that we're going to be using from now on. And then, so I guess we stopped at when we were starting to validate the chunks. And I do want to just take a moment here. I guess last class I had in mind that we had extra 10 minutes that we actually didn't. And so I was trying to finalize everything within those 10 minutes. And maybe I rushed over some of these concepts here. But I just want to, now that we have 2 hours today to work together, I do want to take a little bit more time to just go through what we did here. So, the first, it's always important to validate our clusters, right? And the first step that I wanted to do with the validation here was to bring in the variables that were used to create the clusters, right? So here it's validation in the sense of understanding, okay, we have these clusters here. What is driving these clusters as far as what we use to create them, right? So all of these 4 variables here were actually used to create those 4 clusters, right? Those were the variables that k-means saw when we were training that model. So, we just see here, and then we also had some code where we added the p-value to see if those 2 box plots means were significantly different. And even though the box plot here, the center line in the box plot shows the median, not the mean, but for the sake of this exercise, we can assume that looking at the p-value and that we're comparing the means that are approximately similar to the medians in this case. Anyways. So in my case here, cluster number one had higher shallow and deep ECA, also had higher elevation, and looks like had higher slope as well. So all of those four features are part of cluster one. If you do remember when we did this exercise with the yield stability zones, we only used yield data to create those yield stability zones, right? We did not use any of these terrain and EC variables. And that gave us, it gave us 3 classes or 4 classes because that's how we defined them, right? We could have defined only 2 classes if we wanted, but the goal was to define 4 classes there. But if you do remember, then we have unstable, high stable, medium stable, and low stable, all related to yield, right? And here on the k-means algorithm, it doesn't have to give us 4 zones just to try to see if those would match with the yield ones, right? It just gives us the number of zones that the algorithm thinks makes most sense for this data set. And perhaps if we had brought in more variables here, so again, let's say that we had done soil sampling in a gridded format and we had a whole bunch of like nutrients and organic matter and other soil variables layers, we could have brought them here and they could have changed the way that the management zones look like. It could have changed the best number of K for this example. So it's just something for you to keep in mind that, management zones, if you're creating them or if you're just being handed this type of layer, always keep that in the back of your head that a lot of things can impact what a management zone ends up being. So one of them is the data that's coming in. The other one is how many zones people decide to have. A lot of times when you see, especially I guess like when you go to more commercial side and you see management zones being created, I don't really think that they try to find what the best number of management zones using some type of approach like we did in class. It's more like, here's how it looks like with 2, 3, 4, 10, well, however many, and then the producer does whatever they want with it. So, I just wanted to, again, make sure here that you understand that we're using a statistical technique to define the best number of zones. And that, and that if you're doing science, that's a more objective way that we should be trying to conduct this, but it's done in other ways, less objective in other setups. Okay, so we did have this question here, and again, I just want to say one more time, maybe for you, cluster 1 is all lowest in everything here than cluster 2. That could be the case. Clusters 1 and 2 could be flipped on your side compared to what I am seeing on my screen because of that randomness of the first step of k-means. But in my case here, if we're looking at my screen at least, then we had this question here. If we recall what we saw on the yield exercise and how these same variables were affecting the yield zones, we kind of came to the conclusion that is most likely cluster 1 would be like the highest yielding one, because that's how it was related. These variables were related to the high stable zones. Okay, so if we think of it, this is a concept, I guess, that applies a lot in machine learning, which we did not do here, but I do want to re-emphasize that. To truly validate, so when we look, so you're looking at the variables that we use to create the zones, this is more like just checking how those variables are driving the zones. But now if we want to actually validate those zones, we need to use data that the k-means did not see. So the data that k-means did not use to create these zones. In our case, at least the way I decided to conduct this is using yield data, right? So yield data was not provided to the k-means algorithm, right? K-means did not see the yield data. So by using yield data to validate the zones, we kind of have a more unbiased understanding of what those zones also represent, especially with yield, which is normally our variable of interest. So we already went through this code here, and I'm just walking us through what we're seeing more, I guess, more slowly so we can think more about these, right? But so here I'm basically on that zone SDF object. Let me just print that so you can see. We have we had that cluster number column, but then we also have the standardized yield, standardized yield for 2017, 2019, 2020. We have the mean standardized yield across those 3 years and the CV, right? So on this chunk here, I'm basically just showing you how the standardized yield for each one of the individual years is behaving across the different clusters, right? So in my case here, we're confirming that cluster 1 had significantly highest yield than cluster 2 in all 3 years. Although we do see a lot of variability, right? Perhaps especially here in 2020, we see that cluster 1 is highly variable. And just to refresh your mind as well, the scale here is percentage, right? Because this is not pounds per acre, it's not bushels per acre, it's not none of those units. This is percentage because it was standardized using the median of that year. So this is a percentage of the median. So we just see how, in fact, cluster 1 had higher yield than cluster 2. Then I also wanted to see how cluster 1 and 2 were affected by the mean. So the mean standardized yield across all those 3 years, which is in the column mean pixel, and also the coefficient of variation of those pixels as well. So if you go ahead and run that chunk, we see here that they're significantly different because p-values are less than 0.05. But we also see that, so cluster 2 has a higher median CV, right? We see that by this red line or solid line going across the box plot, but also it has a lot more data points as outliers, right? So it really has some very high CV values, especially cluster 2. So related to CV, right? That's the variable. And then we look at the mean across all 3 years. We really see that cluster 1 has consistently higher yield, even though there are some outliers compared to cluster 2. So I think we probably stopped here, and I do wanna tell you this, because of that random first step of k-means, maybe for you is flipped. So I do want to ask you on your side for you to take a moment here, look at your plots. Perhaps especially look at the mean pixel plot here that's right above you, and just write down here. So to me, cluster 1 has, so higher CV, cluster 2. So cluster 2 has higher CV and lower yield, and cluster 1 has lower CV and greater yield. This is going to be important because we're going to get to the end of this exercise where we're going to recode these clusters. Instead of calling them cluster 1 and 2, we're going to call cluster high and low yield. And for you to be able to do that successfully on your side, you have to know what it is on your computer, which may be different from mine, right? Maybe yours is flipped. And so that's why I'm not giving you the answer here, because it may be different on your side, but I do want you to take note of that here, because we're going to use that information towards the end of this script. Okay, let me see here. So the next thing I want to do here is so I want to calculate so if you think of it, I want to know how many pixels were classified as cluster 1 and unstable, cluster 1 and high stable, medium, low stable. The same thing for cluster 2. So I want to know, like, if we were to bring together the ST class column, which has unstable, high stable, medium, low stable, and we bring the cluster 1 and 2 layers, I want to see how they match, like how many times things happen if we just do a cross of all those variables there. So I'm calling this a contingency table, which, I mean, I guess it is a contingency table, but in the end, I want to plot it. So it's not going to be an actual table when we see it. But that's what I want to do next. So we understand, like, how many pixels in cluster 1 were classified as each one of the ST classes, how many pixels in cluster 2 were classified as each one of the ST classes. So let's do that here so we have a little bit of a better understanding of how these two layers are connected. So we're starting with zone SDF. Let me just bring that for you. We do have a column here, cluster F, that has values either 1 or 2. And we also have a column ST class, which has all the 4 classes that we categorized in the previous exercise. So to do a contingency table between those, let's just walk through some of the steps. So the first thing is we need to know how many observations there is in each one of the ST classes. To do that, so you can start coding with me now. We're going to use the pipe. We're going to do a group by. So in this group by here, we're going to call ST class because I want to group by each one of the ST class levels. And I want to use a, you know what? I'm going to change it a little bit here just to show you something. Let's use this summarize. So on a summarize, I want to call this variable uppercase n, make sure that's uppercase because there's going to be a lowercase one after. And I want to use a function called length that basically gives us how many observations there is in a given column and class. And I just want to say length of ST class. If I run this, this should be, this is what it gives us, right? So it's saying that for high stable, we have 144 cells, low stable for 478 and so on. And one thing to notice is I use summarize, right? So every time you use the combo group by summarize, you should expect that your number of rows will decrease like they did. Zone SDF has like 4,032, right? So we went from that to 4 pretty much because each row is a level within ST class. However, and this is something that I briefly mentioned when we're talking about the midterm follow-up, is I do want this information here, this uppercase N, but I do not want to summarize. I basically want to create this column called N, but I want it to run pretty much for all 4,032 data rows. And every time that it just repeats this number, every time it sees that high class, right? So to do that is a pretty neat trick because you can do that by simply changing the summarize into a mutate. So, and this is what I want us to have. This is what we need to have, but I just wanted to show you the flip side of that. So if I run this as a mutate, I continue having 4,032 data rows. If I go to the end here, I do have an N there, and this N is basically repeating that value for every time. So this, I think, is the value for, let's see here, what was the ST class? That was for the medium stable ST class, right? So it's basically repeating that value every time the cell ST class is equals to that medium stable. So this is a trick that I think is really interesting because we're going to use this to our advantage now. Okay, so I know how many observations there is within each one of the clusters of these spatial temporal yield clusters. Now I want to know how many observations there is between the combination of cluster or ST class and cluster. Sorry, I know that kind of confusing there because they're kind of two different types of clusters, but ST class and cluster, let's call them that way. So to do that, we're gonna do another pipe here. And let me ask someone so based on what we just did, and I'm telling you now that I want to know how many observations there is for each combination of cluster and ST class. Can you kind of help me to think through how we would do that?
We group by cluster.
Okay, so we group by cluster. So cluster, I think cluster F is the name of the column. What now? What after?
I mean, we want the same type of volume, so we can do it.
We could, so I think that is one way, but like, so the way that I'm phrasing this is I want to know how many observations there is, not within each cluster, but within each cluster and ST class. So like I want to have a row that says, or the goal is to, like, if we were thinking on a summarized way, I would have a column saying ST class high stable, cluster number 1, number of observations within that combination of cluster one, high stable.
We can check the what is the distinct number of ends. Like how many of 3 to 4, 8 are there?
We could use distinct, but I think that would like be more involved, like we have to do more coding. So let me, yeah, somebody online?
Could we use like a double group by cluster and ST class?
Yes, that's exactly it. That's where I was going with things thicker. Yes, so we can basically add on this group by as many variables as we wish. I think we haven't seen that yet, at least not in my class, but that's what we need to do here. So if we just do cluster and ST class right there, and so that's the group by, right? So that's the combination we need to have. Then we add a pipe, and we can just so the function tally is basically the same as asking for length. It's just like a shortcut of that. So we can just use tally at this point. And I want to show you what happens. So tally is basically I guess using length gives us the number of observations, but we needed to have as a mutate because I did not want to decrease the number of rows at that point. Tally is like this, but using summarize. So tally reduces the number of rows for us. Okay, so here's what we have. We have a column with cluster, so ones and twos, and then a column with ST classes. So all the 4 classes repeated twice because we have the 2 clusters, 1 and 2. And then we have the lowercase n, which is how many observations we have. So in this case, 139 pixels were classified as high stable, and they fell within cluster number 1. So this is almost what I wanted to have. The only difference here is we calculated the big N, right, which was the total number of observations within each one of the ST classes. And that is not here anymore, because when we do a tally or when we do a summarize, he only keeps the variables you're grouping by and the summary that you're doing. It removes everything else. A neat trick to keep variables that you want to keep is basically coming on the group by and providing that variable that even though you're not grouping by it, but you want to keep it. So if we come here and we say n, uppercase N, and we do this, it keeps that uppercase N for us in the data set, and then we also get the lowercase n coming from tally. So what I want to do here on this contingency table, this is pretty much a contingency table already on its own. However, the reason why I calculated the uppercase N is because I do want to calculate this ratio here. I want to calculate this proportion of how, like what percentage of points were classified as high stable and fell in cluster 1. So to do that, I basically want to do lowercase divided by uppercase. So I needed to have the uppercase N in the data still to do that calculation. Okay, so let's calculate that proportion next. So let's just add a pipe here. Let's call mutate. I'm going to call this prop for proportion. And then you can just say prop equals open and close parentheses. So we have the ratio inside of the parentheses, which is basically just lowercase divided by uppercase N. So lowercase n divided by uppercase N times 100. So if we run that, now we have this proportion of how many of the ST class by cluster fell within each one of the ST classes. And this, it's already, I guess, we already have that proportion here, but every time I can, I like using plots. So let's go ahead and create a plot here. So let's feed this, use a pipe and feed that right into a ggplot. So we're not saving this result in an object. We're just doing that on the fly and just feeding that into ggplot. Within ggplot, we ask for the AES function. On the X, I want to have cluster F, right, which is a column. Is a column right here on this incoming data. On the Y, I want to have the proportion, so it's just called prop. Let me break code here to make it easier. And I do want to fill by cluster, so you can say fill equals cluster underscore F. And then here, the way, I mean, you know already that if we just run at this point, there's not going to be anything in the plot because we haven't asked for anything yet. So let's just add a plus after that ggplot and add a geom underscore col for columns. If we run, so there's a lot of stuff going on here if you think of it. So within each one of these bars, there are all the 4 ST classes. I do want to change that a little. So I want to facet that. I'm gonna add here a plus and then use a facet underscore grid. Give the tilde to say by and then ST class. So this is basically gonna create a facet for each one of the levels of ST class. So if you run that, this is what we get. Just gonna leave some of the code there for you to see. So what we're seeing here is we're basically, for each one of the yield stability zones, we're seeing within that zone, how many observations were cluster 1, how many observations were cluster 2, right? Because here it just gives us an idea that even though if we just look at cluster 1 and 2, at least on my side, cluster 1 has highest yield and lower CV, but we know that because we only have 2 clusters, they're mixing that yield data that we had before because we had 4 classes, right? So there is no way that 2 classes can represent 4 classes well. There's going to be some mixing there. And I just wanted you to see this so we can understand better what's going on. So where we had that high stable area, when we looked at the yield data, about, I don't know, 90 some percent of the high stable pixels were considered cluster 1, which I guess kind of comes in, in the same idea that we had when we looked at the yield data by itself when we were validating just above. When we look at the low stable, most of the pixels that were considered low stable fell within cluster 2, right? So this is also like maybe 97%, so pretty high. We see that medium stable is it's pretty mixed, right? So probably like about 60% of the medium stable pixels fell on cluster 1 and another 40% on cluster 2. So this is something that our clustering algorithm with 2 management zones cannot handle, right? It's going to mix that. Yes, David. Yeah. Yeah. And then we see that the unstable pixels fell mostly within cluster number 2. So we do see here cluster number 2 being low stable and unstable. So low yielding points and also unstable points. And most of the high stable ones being in cluster 1. So this is just a different way for us to look at this and see how many times those 2 layers co-occur in different places. So again, so I do on my complete code, I do have some more information here. I guess this is basically what we needed to interpret it. Then the code that I will share with the complete code just has some extra, aesthetics, I guess, changing, but we can skip that for now. And so based on this, again, on my side, I do want to call your attention again on your side. So on my side, again, cluster 1 is high yield. Cluster 2 is low yield. Make sure, don't just copy what I'm saying. Make sure to check your plots because in your case, it may be flipped. Okay, so basically we develop the clusters, which at the point when we develop them, they're just 1 and 2, A, B, right? They have no meaning. We have to bring variables to understand what's driving them, and especially yield variables to understand if they represent high yield or low yield zones. So we just went through that. Again, on my side, cluster 1 is high yield, cluster 2 is lower yield. And this is going to be important information next because we're going to export this layer to file so we can use this when we're creating variable rate prescriptions. So if you come here on the next chunk, I'll just add a pipe there. So right now zone STF is our last data set, right? So it has the cluster 1 and 2, it has all those columns, so on. I do want to create a new column here. So let's use a mutate, and I want to give this column the name of zone. So zone is going to be, I want to basically use the information we just decided up here and say, if cluster F equals to 1, then zone equals to high. And this is yield zone, right? That I guess I'm using the word zone, but I'm referring to a yield zone. So yield zone is going to be equals to high, and if cluster F equals to 2, then zone is going to be equals to low. How can we do that?
This one.
Case when, yes, we can do case when. In this case here, we could have used if else because it's just two conditions. I mean, just one condition and two outcomes. But case when is a good one as well. Let's go ahead and use case when. Let's hit return. So let me ask someone else. Bo, how would you specify that condition?
Would you do it based on cluster name?
Yeah, so one way to think of it is you have to use column names to refer, right? So this is the data that we have. So I want to say if cluster F equals to 1, then zone should be considered high. And if cluster F equals to 2, then zone should be low, right? So how can you help me maybe to write that first condition there?
Us to like cluster F
Mm-hmm.
equals 1. You say to do that,
Yeah, we use that tilde to say then, right?
would be, high yield.
Perfect, awesome. We can just call it high just for short, but that was it. Thanks, Bo. Okay, so that was our first condition. In this case, we only have two conditions. So the other one, I'm just gonna copy this and just give a comma and say if cluster F equals to 2, then zone equals to low. And again, I just want to say this one more time. Make sure that this is actually what is on your side. That cluster 1 was the high yielding one and cluster 2 was the lowest yielding one. On your side, maybe that was flipped. And you can confirm that if you just look at this plot up here. If your side was flipped, then you would have you would basically be flipped to what cluster 1 and 2 are on the high stable and low stable here. So make sure that's right. If we just run this, we're now saving this to an object, so it's already just printing for us. If we go to the end, now we have this column called zone that has only two values, either low or high, based on that cluster F column. Okay, so now that we have created that column that basically tells us what cluster, that we validated the cluster with yield and what that cluster represents with yield, what that zone represents. Let's export this to file. We're going to use a function, called write_sf, as you're probably.
Hey, Dr. Bastos,
Yes.
I had an error in that last jump.
On this one?
It says that the error was caused in the case when function.
Okay, so a couple places that case when can give you issues. So when the mutate here is just one equal sign, but inside case when is a Boolean operation. So we have to give it two equal signs. Make sure you have those two. Make sure you have the comma after the first condition. And then make sure you're closing all the parentheses. So there is a parenthesis called closing case when, and then another one closing mutate.
Got it. That was where it was. Thank you.
Awesome. All right. So let's continue exporting this. So the data is basically already what's coming through the pipe, right? So we don't have to give a an object name here. We can just go ahead and give it the path. So let's open and close quotation marks. We want to get outside of the code folder. So // hit tab. We want to go inside of the data folder. And then I want to call this object zone_s.geojson. And always that every time you're using the write_sf function, make sure that you change the argument delete_dsn to be equals to true. If you don't, I just want to tell you again, we found this out last year when we were doing this class, where like I was running the same script maybe a couple times, one when I was developing and then one in class with you all. And then I noticed that without this delete DSN, if I wrote this chunk twice, so zone SDF has like 4,032 rows. If I run this chunk twice without having the delete DSN, the object that I save actually has twice as many rows. It's basically appending every time that you're writing. So, and that's not what we want, right? So to avoid that, just make sure that we use delete DSN equals true all the time that you're using write_sf. So if you just go ahead and run this, you go to your R blue button, you go to the data folder. Now you should have the zone_s.geojson file right there. And that's going to be important because we're going to bring that in our next exercise, which is the variable rate prescription exercise. Okay, so today, or I guess not only today, but for this entire management zone creation exercise, we learned about k-means and how it works. We learned about how to find the best number of k for our data set. We decided to go with 2 zones based on those algorithms. We explored the main zone drivers, right? So the variables, both the variables that we use to create the zones, but also the variables related to yield that the zone algorithm did not see. Then we validated with those yield areas and then explored the main instability drivers of those zones. So the next step of this entire workflow here is for us to basically create the some variable rate application using these zones. And that's going to be our last exercise, at least with the data we have for this field. That's basically going to wrap up most of our course. And if we just like take a step back and we just think through it, of all the process of getting raw data, maybe from a producer, maybe from a consultant, maybe you're collecting that for your farm, getting all the raw data that you're going to be running into in research and commercial settings, we went through processing that data, processing as far as filtering the yield data, cleaning, wrangling, interpolating, doing that with yield, with EC, doing that with terrain. Of course, if in your work, if you have other layers that are also geospatial and you can do that like soil data, you can also incorporate the same concepts there. And then bringing them to create zones and now validating zones and then finally creating a variable rate prescription, which is a very common workflow that you see in Precision Ag. So we're just almost at the end of that. We just have one more exercise for that. Okay, so if you haven't yet, just make sure you save your partial script by clicking on that save button. I do want to talk about the assignment before we start the variable rate exercise. So there is an assignment here. I want to show you, so it is on GitHub. I guess I can leave this open. Let me just go to that. So I posted on GitHub. It is on our so it would be under assignments and it's assignment number 8. And I have a QMD for you right there. So you can download that, whenever you want, but I do want to show you what I want you to do and how I want you to do that. So this is the QMD that you're going to see on our side. please make sure to follow the instructions. When I'm grading everything, I do have fields for, did the student add their first and last name in the author page or in the author line or things like that. If I am asking you to do something, you will be graded on it, even if it seems pretty silly. So if you don't do it, you're just missing points that are, you know, that you could have easily not lost. So make sure you add your first and last name there. And so this assignment here is basically, I'm asking you to play around with the focal window that we used. I want you to play around with a few different options of matrix size. So I'm gonna ask you to be creating a matrix of size 3 by 3 instead of 5 by 5 as we did in class. And also play around with the summary function type. In class, we use the mean. I'm gonna be asking you to play around with that as well. So I do have some instructions here, make sure you follow them. And I am telling you what I want you to run. So I am telling you here that I want you to run the 3 by 3 with a smooth function of mean, 3 by 3 with minimum, and 3 by 3 with maximum. And then for each one of these 3 scenarios here, so if you think of it, you can, if you want, you can just use the script we develop in class. Let me just open that here. You can just use the same script. The only thing you're gonna change is on this part of the code, right? So you change what I'm asking you to change on this part of the code, you run it, and then you make a plot. I want you to create this plot and export this plot. Make sure that when you're creating the different plots coming from the different options that you're running above, that you also rename the title, because that's what it will allow you to visually know what's the result for each one of the options I'm asking you to run, and then you can comment on them. So the first step would be for you to create the different options I'm asking you and export these as PNGs. Make sure you also rename the file name here when you are exporting, because you're gonna need to know that file name. It's gonna have to match what you did so you can do what I'm asking you. So you're first gonna have to do that. And then I want you to embed the PNG. So this script, this QMD with the assignments, you should not be coding here. There's no code going here. All I want you to do is to edit the code that we're using in class, create the PNGs out of that code. And then in this here, basically what you want to do is just, so wherever you save your A8 questions, let's say that you save this A8 questions QMD in the code folder for the project, for the management zone project. If you do save that in the code folder, maybe I have that here. No, I don't. If you do save here, all of your images are going to be on your output folder, right? So for you to bring in an image into a QMD file, I already left you some of the structure to make those plots be side by side, so you don't have to worry about that. But for you to bring an image here, you're gonna have to come in between the parentheses here and then just navigate to wherever that is. I'm going to navigate to somewhere a lot farther away from if you bring the QMD into the code folder of the management zone project, you're just gonna do / and then you're gonna be on the code or output folder, and then your image should be right there, right? In my case, this A8 questions QMD for me is not in that folder, so I do want to navigate somewhere I can find an image just to show you what I'm expecting. So when you bring that in like this, it basically just brings that image. I do want you to I'm bringing here the same map. Of course, in your case, you would not be doing that. You'll be bringing the different maps that I'm asking you on the instructions on a way that when you render this, let me just render so you can see. It will render in this format where the maps are almost side by side, right? But in this case, it's the same map just repeated. On your side is going to be one map is going to be different from the other based on the instructions I'm giving you. And then I have a few questions for you here. So to successfully complete this assignment, you have to first change the code on the class script, create all the maps I'm asking you to create, and then bring them successfully here. If you cannot bring the maps into the assignment, you're not getting full grade. You have to do that successfully. I just showed you how to do that. I left you most of the code to do that. You just have to make sure you bring in the proper files and then answer the 3 questions below. I am asking you to send me the HTML render version of this. Make sure you do that. If you cannot, for some reason, let me know, but I am expecting the HTML. Yes,
So as far as the maps go, there should be 5 total, 2 of which is already done, and then 3 of which are going on.
that's exactly it. Yeah. So yeah, Bo was just, I just want to rephrase that for those online. So all the 5 maps that you're gonna have to bring here, 2 we made in class. So 1 is the unsmoothed, 1 is the smooth with 5x5 and mean, and then the 3 others are the ones I'm asking you to create to play around with the focal function. Any questions about this? So I do have this due on Monday, April 10th at 11:59 p.m. So make sure you do it by then. It should not take you a lot of time, I don't think. And also don't forget to answer the 3 questions I had for you after you bring in the maps. All right, so if we don't have any questions about this, maybe we can take a 5-minute break and then come back to begin the VRN exercise. So let's be back by 10:02. Let's do that. 10:02. Put a time.
Excuse me, Professor?
Yes.
Yes, so I'm having trouble with some of the packages, so I was not really able to follow today, especially with dplyr. I don't know what's going on. It tells me that rlang is not loading. It needs a higher version, but I was trying to troubleshoot it, and I went on RPlan website to install the latest one, and I had the latest one. It says, so I have 1.0.6 and it asks me for 1.1, which is not even available on our grand website.
So rlang, is that the package?
So when I load the dplyr, it says package or namespace load failed for dplyr because namespace rlang is required, the higher version is required.
Did you try to just do a install packages, like install dot packages Erlang?
Yeah, I did. I can do it again.
Yeah, that is, I'm not sure what's going on there, but
Yeah, it says object Erlang not found.
did you have Erlang in quotation marks?
Yes. So, it is updating.
All right, let's see if that
I
works.
see that. It says analyzing install packages, updating loading packages, and it keeps on asking me to restart my R.
What if you just, I mean, it's asking you to do that probably because like it's installing packages that you already are using in that R session. So that's why it's
Alright.
asking you to do that, I think. So what happens if you just say like, no, don't restart?
Yeah, I did that and it successfully installed Erlang, but when I load again dplyr, I get the same error that I was getting at the beginning, that higher version of Erlang is required.
Okay. So I'm not gonna be able to troubleshoot that right now, unfortunately, but we can connect afterwards and I can try to help you there.
Alright, sure, thanks.
All right. I'm just gonna give it another moment here and then we'll get started. All right, so let's get started here. Again, if you're online, make sure to turn on your camera. So I have uploaded to GitHub another script. So if you want to go ahead and if you have not done yet, if you have not downloaded the GitHub repo this morning, please go ahead and do that. You're gonna find a new script on the class code folder. That new script is called 0405 zone VRN partial. What I want to ask you to do is, so first download the repo, so you have that script on your computer. And then on your main class folder, I want you to create a new folder called 09 zone VRN. So this is going to be a new project, right? So it should be you should be at the same level as where you're seeing your previous projects. So create a 09 zone VRN. I'm going to open that up here. You know the drill already, but just to refresh, create the code, data, and output subfolders. Bring that script that I just uploaded to GitHub into the code folder, and then launch NER Studio window, and then create a new project. So you know how to do that, but just launch NER Studio. You can click on that icon, project icon on the top right, and then just do new project, browse to that folder of this project that we're just talking about now, and create at that level. So you should, in the end, you should be seeing this on your side, and you should have that script inside of the code data or code folder. Which is All right, I'm gonna give you just another moment here and then we'll get going. All right, so if you still need another moment, it's okay, because we're gonna be talking a bit before we start coding. If by the time that we start coding, someone still needs more time, just let me know. So on your side, maybe your RStudio project has already launched when you created it. On my side, I haven't launched it, so I'm gonna go ahead and click on that RProj icon to launch it. If you're not seeing this script yet, you know how to do that. You can just, making sure that you are in the right project, you can come here on the Files tab, click the R blue button, go to your code folder and just, click on the partial script that will make that pop up for you on your RStudio. And this is what you should be seeing. Okay, so I do hope we can, if not finish this exercise today, get very close to it, very close to finishing it. But we do need to finish this by next Friday, and we will, because next Friday I will basically give you everything you need for the final project. And you're gonna be able to get started on that. And then you're gonna have a couple weeks with Dr. Lacerda talking about UAV imagery, how to stitch that, how to process that type of data. So you're not gonna be seeing me for the next couple weeks. So I do wanna make sure that we go through all this and finish in time. Okay, so this exercise here, so all the way that we've been in the beginning, and we got to this point where we have the zones of high and low yield zones. And now we're gonna use that to create a variable rate nitrogen prescription based on those zones. That is one approach of managing nitrogen. You could also use that similar zone approach to manage other nutrients, especially phosphorus, potassium, pH through Lyme application. So there's a whole bunch of things you can use the same approach to manage. I'm going to show you an example of using nitrogen management more specifically. So the goals that I have for us today is, to begin with, how do you define what rate of nitrogen fertilizer a crop needs? So we're going to first go through that. How do we find that information in general, but also specifically for Georgia and for cotton, which is the crop we're going to be working with here. Then we're going to understand what about nitrogen management that we need to know in order to be able to come up with a variable rate or with a rate of nitrogen for cotton. Then we're going to estimate zone-specific cotton yield potential. That's going to be an important piece of defining nitrogen rate. Then calculating zone-specific total nitrogen recommendation. And then from that, calculating zone-specific side dress variable rate nitrogen recommendation. And then at that point, we're going to know, okay, we need this much fertilizer to be applied to this part of the field. But then if you're taking this to a producer, they're going to ask you, well, how much fertilizer do I need to have by my field that day? So I can plan ahead. So we're going to see how can we then go from rates to calculate total gallons of fertilizer that we need to order to have by the field. And then we're finally going to export this file here as a shape file for the first time in this course. To then you can give this shape file and all the accompanying files to whoever will be making that variable rate application. So this is what we're going to be doing on this exercise. Okay, so we again are going to be working with variable rate nitrogen fertilizer recommendation. Specifically in cotton, where we're going to have a different rate for each one of the zones that we just created. Now, how do we know how much nitrogen cotton requires? And if you think of it in a broader way, how do we know how much fertilizer of any sort any crop requires, right? So normally this information comes from research and especially from extension bulletins or extension publications. And normally, especially when we're talking about the US, each crop and each state have their own recommendations, right? So if you go to Florida, maybe their algorithm to recommend action for cotton, which I don't even know if they have one, may be different, right? And if you go to the Midwest, it's going to be different. And each state has their own. So if possible, and if doing this in the US, we do have the universities providing this type of information everywhere that crop is an important crop for that state. So the first place that, and I'm telling you all this just so you know, so I don't come here and tell you, hey, this is the algorithm we're using for nitrogen recommendation. That's it. At least you know if you're doing this for any other crop, any other nutrient, any other state, you know how you should approach this if you're trying to find how do I determine this rate to begin with, even if it was a fixed rate. How do you define a fixed rate of nitrogen in a field for cotton? So if we just, so what I would do would just basically Google, right? So something like cotton nutrient recommendation in Georgia, right? So you do have to be specific with the crop and the state when you're doing that query, if you're in the US, because that changes from state to state and crop to crop. So if we just went to Google and search for something like that, you would come, we will have some results, right? So here in the state of Georgia specifically, UGA publishes the Cotton Production Guide. If you have not seen this before, this is a very extensive production guide that has a whole bunch of recommendations for growing cotton, and fertilizer recommendations is one piece of that guide. So I left you the code here. I just want to copy this and paste that into my browser so you can see the guide. So you have the link on your for your records as well. So this is a PDF that you can download if you wish. But again, it's a Georgia Cotton Production Guide. I believe it's updated every year. I don't think that the 2023 is out yet. It probably released at the end of the year. So the 2022 is the latest one that we would have. Oops, I clicked the link. Let me go back. So again, this is a very comprehensive guide for a whole bunch of things related to growing cotton. And it is from UGA. We would basically be looking under the fertilization topic, we would be looking for nitrogen management, right? So this is, I think it's on page 9. So I'm just going to scroll down to that page so you can see what it is saying. So right here starts nitrogen management. So it has a whole bunch of explanation of what we should be looking at and considering when coming up with a rate for cotton in Georgia. One of the main drivers is going to be yield goal, right? So if you get to that producer and you say, what is your yield goal? It has to be something realistic, right? So if you go to a field that is dry land and maybe, doesn't have a lot of yield potential, if a producer tells you that they want a yield goal of 2,000 pounds of lint per acre, that's probably not very realistic, unless they really show the data. Maybe they're in the part of the state that gets a lot of rain and has a great soil, that they still get high yields from a dry land situation. But I guess what I'm trying to say is the number that we use here to define our yield goal has to make sense for that field, right? So we would go to that field, you would try to understand what is the yield potential of that field, and then basically use that yield potential as the yield goal here in this table, and we'll relate that yield goal to a given nitrogen rate. And then here, it does have some other considerations. So it's saying here that, so you come up with this rate first based on your goal, and then you adjust that, you may adjust that based on a few different aspects. So you may increase this N rate that you find on this table by 25% if you have deep sandy soils, if it is cotton following cotton, or maybe history of inadequate stock growth. And you may decrease this rate by 25% under these other conditions here. So if you have a legume crop coming before, so soybeans or peanuts, if you're cotton following good stands of winter legumes such as clover. So if you do have some other source of nitrogen that is not coming from fertilizer, in this case coming from previous crops, or maybe history of rank of excessive vegetative growth. So if you end up working with cotton and management and fertilizer is part of it, which most likely will be, I do recommend you going through this in more detail and reading more about this and what impacts. Our class is not necessarily about soil fertility and nutrition, so we're not going to be talking a whole bunch about this in this class, but I did want to show you where to find this information if you are doing this work in Georgia. Okay, so if you were to read that table and that page in more detail, you would find again what we just talked about, that nitrogen rate depends on yield potential. So the more yield you want to have, or the more yield potential your field has, right? Not just you want to have, because of course, if you want to have excellent yield and your environment doesn't allow for that, then you're just spending money. But the higher yield potential, the more nitrogen there will be, it will be required, and then you may adjust that in 25% plus or minus, depending on certain conditions. And also, I guess something that I skimmed over, forgot to mention, but one of the recommendations here is that total nitrogen rate. So this is the total nitrogen rate on this table. That total nitrogen rate should be split applied. So part of it should be applied at planting or near planting, and then the remaining at side dress. Right. So this is also an important piece of information for managing nitrogen in coffee. Specifically for UGA, we also have another resource that I want us to use, especially for this exercise and in the future, which is called UG FertX, which I think is probably University of Georgia Fertilizer Extension or something like that. I did leave you the website here. I just want to launch the website. So you can see it is a more interactive way of determining fertilizer rates for different crops in Georgia. I do want you to pay attention here because you will be using this on your own as well. So it has a handful of different tabs on the top here. Really where you would go is inputs. So here on inputs, I mean, if you do want to complete everything, of course, you're welcome to. But some of the things that we want to change, so one of them is crop, right? So we want to say, we want to have cotton listed as our crop. So the soil type here, I am assuming that our field has a coastal plain type of soil. That's an assumption, but that's what we're going to go with. If you're doing this for a producer, if you enter the county here, I think that would basically help you to decide for you what soil type it is. But we're going to go with coastal plain for this case. This field is irrigated, so I want to check that box. And that basically, what that changes is just this tool here gives you already an estimated yield goal by default. Of course, you can change that, but that is one of the things that changes when you say irrigated. By default, it increases your yield goal. And then prior crop, you can either leave as unknown, or you can, if you know what was the previous crop, you can say that here. Again, if that is a legume, it will change your recommended rate in the end. I really don't know what this field was. I just want to say, well, let's say, because if you think of it, we're doing this for, let's say, this year, like 2023. I don't know what they planted last year. I want to assume it was cotton, but I'm making that assumption. If you don't know, you can just say unknown. But I want to assume it was cotton as well. And in our case, so this tool here is giving you recommendation for a whole bunch of nutrients and also lime application to manage pH. We are not going to do that in this exercise. I'm just showing you this so you know how you would use, especially for nitrogen. We're not going to be talking about other nutrients. So really the only thing that is left for us to change here is our yield goal. Even though it is already given us a default yield goal, but we're going to be changing that, right? We need to find a reasonable yield goal for the different zones, right? So we know the zones yield differently. That is the main variable coming from the zone that will impact what this number is for each one of the yield zones and what the recommendation is in the end. Okay, so going back to our script. I just had you here. I was just asking you to play around with that. And I do have a quiz. Right, so that we're gonna do right now. So using either the tool that I just showed you or the guide that I showed you as well, where we will look for this information, I want you to answer a couple of things for me here. So question number one is list at least 3 required pieces of information that we need to make a recommendation of nitrogen in cotton. There is more than 3. I just probably mentioned 4 or so. These, you can find these either on what we selected and clicked, or maybe on the guide if you want to read that. So you just need to list them. And the second part of this quiz is related to yield potential. So yield potential is one of the main factors affecting the recommended nitrogen rate. How can we, I want you to tell me here, how can we define yield potential for each one of these 2 zones? I want you to think about, when you're answering this, I want you to think about the data that we have for this field. So I'm giving you this data, all this data we're working with in this class is all for the same field. Based on that field, how would you determine yield potential for the different zones? So I'm gonna give you 5 minutes here. Just send me by email your answers. Don't overthink it. It's pretty straightforward. Yeah, let me just put 5 minutes here on the timer, and then I'll be waiting for answers. 1 minute left. And this is will also be your attendance for today, just to. All right, time is up. I know some of you are still working on it. I want to continue here. But just make sure you send your answers soon. Okay, so one of the, so most of you, at least I was looking at some of the emails coming through. So most of you had in your answer yield potential as that required piece of information, and that's, I mean, basically all the answers that you were giving me were correct. So yield potential is probably the most important one. Soil type is important, previous crop is important. One thing that I don't think any of you mentioned, but probably because I didn't emphasize enough, is we have to define what split are we going to do between pre-plant or at planting and side dress, right? So that is one thing that we will have to think about when we get to that part of the exercise. So that was another one as well. But yeah, I mean, a lot of things are impacting this, and yield potential is probably the most important one. Okay, so on the second question here, if you think of, so some of you answered, oh, we can use the historical past yield data that we have for this field. We can use the average, we can use the median, we can use some quantile. Those were some of the answers that at least I was able to see until now. And those are all good guesses, right? I mean, the layers that we can use for this field specifically are the yield data, right? So we do have the yield data for this field for 3 years. We can use that. So let's actually do that here and import those layers so we can do, we can estimate the yield potential based on them. And when we get to that point, then I guess we have a more conversation about if the mean or median or a given quantile is the best. So if you go ahead and run the setup chunk, I left you all the packages you needed there. I also left you here the defining theme for the map. You can just run that chunk as well. And the next steps here is basically chunks to bring in the data for each one of those years. So the first one here, if you want to go ahead and start coding with me, we're gonna bring in the interpolated, so the wrangled, clean, interpolated yield data for all 3 years, beginning with 2017. So let's just come down here, use that assignment symbol. We're gonna use the function read_sf because that version of this data is a .geojson file. Open and close quotation marks. Here, you're gonna have to see where that path is on your computer, right? So right now we are inside of the code folder of the 09 zone VRN project. We want to get outside of the code folder. So // hit tab. We want to get outside of this specific project. So // again. You should at this point be seeing your main folder of the course. The data that we're after is on the 04 yield monitor project. so you have to go to that project. If you name that differently, you have to assess how that fits your situation, but this is how it is on my side. The data we're after is inside the Zero4 Yield Monitor project, inside of the data folder. So if you hit tab again and go on data. And then finally, what we're bringing here is the yield 17 underscore interpolated.geojson. So that is the file that we need to navigate to and bring into this project. If you can do that successfully, the chunk will work fine. If you print it, you should have 4,032 data rows. And we have two columns. So one is called IP yield underscore pounds per acre, and the other one is geometry. If we just quickly check here on the first panel when we print, this should already be in UTM zone 16 north. And I do want to do a quick wrangling right here on this chunk. So after the read SF, I just want to add a pipe, hit return, and I want to use a dplyr select. So dplyr : select. Mostly, I mean, in this case, well, so what I want to do is bring in these two columns. So I guess the select wouldn't really be necessary to use here because we only have these two columns. But I do want to use a select to rename this first column here. So I want to rename that to yield 17 underscore LBAC. So yield 17 pound per acre is going to be equal to that current column name, which is on my side IP yield underscore pound per acre. And then I also want to bring in the geometry. So basically we're using select here just to rename. But if you run it, you should now be seeing a column called yield 17 pound per acre. This is going to be important to rename at this stage because we're going to have yield data from 3 different years and they all have the yield column named the same. So we need to change that at this point. All right, so if we move down to the next chunk, it's basically the same thing. I left you the code. However, you know, the code will for sure work on my side. It may not work on your side if your folder structure is different, if your folder names were different, if you have uppercase, lowercase differences, that would affect it. In which case you would need to adapt this path here. But make sure that now you're bringing that yield 19 interpolated.geojson instead. So for me, this is the path. I will give you a moment to figure out your own path to bring in, but just make sure you're bringing that yield 19. It should be the same path as the one that you used above. The only difference would be the data. You would change the yield 17 to yield 19 instead. So find your path, and then I just want to show you here. If I just read this in before doing the select, I think this has 3 columns. So in this case here, the select is leaving out that var1 var and is also renaming the IP yield pound per acre to yield 19 pound per acre, right? So notice that now it's yield 19, before was yield 17. So make sure you bring that in. It should also have 4,032 data rows. It should also already be in UTM zone 16 north. And then finally, we're going to bring in the 2020 yield data, right? So you can go ahead and do that as well. If you have to fix your path, just make sure you're bringing the yield 20 interpolated this time. And then here on the dplyr select, we're also renaming that to yield 20 pound per acre so we can differentiate the years. So I'm going to run that on my side as well. Okay, so we basically, the goal here that I have is to bring in these interpolated yield maps from 3 previous years, where I do want to call your attention to, because it's been a while since we saw these layers. These are not percentages anymore, right? These yield values are pounds per acre. We've been working a lot with the mean pixel that was like the mean of the standardized yield that was a percentage. Now this is not a percentage anymore. It is pound per acre, because that's what we need to know if we want to calculate yield potential as pound per acre. Okay, before I move on, I just wanna allow a moment of silence, I guess, from my side and ask if is anyone having issues importing these layers? These are the beginning, we have to have them for you to be able to work. If anyone has issues, please speak up. We can try to troubleshoot them. Yes,
Mine just says for yield matching, it says error in select.
on the EL19. Okay, so what you can do is if you just highlight the read SF, so do not include the pipe, do not include what comes before, and just run that. That is gonna show you how that comes in, and it's gonna show you the column names that it has. So if your select is giving you an issue, maybe it's because your IP yield pump breaker was named differently than mine. Awesome. All right. So I don't hear anything else. I'm assuming everyone is good and we're gonna keep moving. So here's my goal. I want to combine these three different, so I want to have one object where we do have the geometry, but then we have the yield 17, yield 19, and yield 20 columns all side by side in one object only. That's what we're going to do next. And I want to ask for some people's or someone, if someone can help me here. How can we do that?
ST join.
Oh, yes, we're gonna use ST join, but I just noticed here, we actually need to bring something else before that. So yes, hold that thought because we're gonna get to that on the next chunk here. So, okay, I was thinking ahead of myself here. So we do, I guess I'm just trying to walk you through my thought process here. So we do need to have those three columns side by side. We also need to have a column with the zone, right? So now, I mean, thinking of the zones that we created being high and low, we need a column with that information. So we can connect the yield across 3 years with those zone classifications that we just did on the previous exercise. So that's actually what we have to import that as well before we join all of them. So in this next chunk here, I'm calling this zone underscore ST. You can use the assignment symbol. We're gonna use again read underscore SF. And open and close quotation marks. You're also gonna have to browse to another project, but now it's the project that we just finished before starting this one. So // to get outside of the code folder, // to get outside of the 09 zone VRN project. I'm seeing now all the projects. We need to go into the 08 management zone one. We need to go inside the data folder, and then you have the zone underscore s.geojson. So if we bring that in and we print it, it has a whole bunch of information. And I just want to make one point here that, you know, I mean, we do have columns here for S, so standardized yield 17, 19, and 20 in the zone ST object. Why can't we just use those columns? Why do we have to bring the yield data from the 3 previous years individually? Why couldn't we just use these 3 columns instead to define yield potential?
Because they have different medians and they were standardized based on the medians of the respective years.
Yes, that's exactly it. So thanks, Ekar. So these columns here are standardized, right? So they have been divided, the actual absolute yield in pounds per acre has been divided by the median of that year. And also which makes this unit here a percentage. So this is a percentage, and I cannot just use percentages to determine yield goal. It has to be pounds per acre. So that's why we cannot use these. So really from zone ST object, I want to do a select here. So if you right there, just add a pipe, let's do a dplyr select again. The only thing I need from here is the zone, right? So we have that column that we created just a moment ago called zone that has values either low or high, and the geometry. That's really all we need from this. We don't need any of the other information. So if you run that and you print it, you should have, again, 4,032 rows. It should already be UTM zone 16 north. And now we only have those two columns, zone and geometry. And do notice here how, like, for each one of these 4 layers, I was checking what was the CRS, if they were matching, if the number of rows was the same, 4,032 for all of the 4 data sets. If none of those are matching with yours, then something went wrong at some point and you would have to fix it, because the way that we built these layers are that they are matching CRS and they have the same number of rows because we use the same grid to interpolate them. Okay, so basically we have all 4 pieces of information we needed. If you come here on the next chunk, I think I actually left all of it for you. So I just want to show you here, we're starting with zone ST, so the one that we just brought above with zone and geometry. And we're merging that with yield 17, 19, and 20. We're using ST join, right? And changing that join to be ST equals and left equals true. So it does a left join. If you run that and you print zone yield, it should still be UTM zone 16 north. And now we should have the following, the following data. So zone, geometry, and then yield in pounds per acre for 3 different years. Excuse me. Okay, so we basically have all of the columns that we needed to calculate zone-specific yield potential, right? So let's do that below. So on the chunk below here, my goal, and let me tell you step by step, just so you also follow what you would have been doing if you were doing this, especially for a grower. So we want to first calculate that zone-specific yield potential. And I do want to propose here that we use the 90th quantile of the yield distribution across all 3 years. And I'm saying the 90th quantile, I guess, just to some extent, that number is subjective, but I'm not using the mean or the median necessarily, because we're using 3 different years, right? So if one year you had a better weather or management or whatever it was that you have higher or lower yield, if we get the mean or the median, you'd be shifting that because of that variability across years. And also because if you think of it, the mean or the median or of a field is really not the potential of that field, right? It's the mean, is not, the potential would be closer to the maximum. Of course, we don't want to get the maximum itself, but I think that, and I've seen this in different extension publications, using the 90th quantile is a good approximation of the potential of that field. So that's what I'm proposing as, so using the yield data, and then the metric that we're using is the 90th quantile of that yield data. Then we're gonna calculate the total nitrogen rate using UG Vertex, and then adjust that in 25%, assume that we're using 1/3 pre-plant or at planting and 2/3 of that total rate to be applied side dress. And then I want to propose that we use our nitrogen source as urea ammonium nitrate. So we're going to go from pounds of nitrogen to pounds or gallons of UAN, which is the actual source. This is important here when you're doing recommendations, because you can provide a map of pounds of N per acre, but that is not the map of product that's going to be applied. It's just the nitrogen itself. So you have to transform that to a product that has a specific nitrogen concentration. In our case, UAN is a liquid fertilizer that I'm proposing we use the one with 28% for this exercise. And then at the end, if you think of it, you're going to come up with a map that says you're going to be applying X gallons of UAN per acre in this part of the field, Y X's of gallons of UAN per acre in this other part of the field. But you still need to let the producer know how many gallons per acre they need total, right? And that takes into account the area that you're applying and what the rate you're applying of that product. So we're also gonna calculate that, so we know, we can tell the producer, you know, we should have X gallons of UAN by this field if we want to do this application. All right, so we're gonna do all that in the chunks below. Actually, in two chunks for now. Before we get to actually doing that, I want to make a plot to show you a little bit of the thinking behind why using the 90th quantile. So our data set that we have here is the zone yield. Let's begin with that. I want to create a density plot to see the distribution of yield across overall and also across the 3 different years. So right now, zone yield, let me just show you. Zone yield has the columns yield 17, 19, and 20 all separate. I want to have all these yield values in one column only. So I can plot that as one distribution. How can we do that? Let me ask if someone online can help me here. Umar, what do you think? What function do we need to change this data format? Did you hear me? I mean, you're muted, so I'm not sure if you heard me, Umar.
Yeah, I did hear you.
Okay. It is a function we've
Sorry.
used already. Yeah. Let me ask someone else. Maybe someone else can help you. Let's see, Sarah, you have any thoughts here? If I want to take these 3 columns and instead of having the yield values across 3 columns, I just want to have one column with all these values in one column only. What function can I use here?
We use pivot.
Can you say that again?
Can we use pivot?
Yes, pivot, right? Yes, thanks, Sarah. So we've been using this in previous exercises. So we want the version that's called pivot longer, because if you think of it, we're going to take these 3 columns that are side by side and put them below each other. So the data is going to increase 3 times in number of rows. So we're going to pivot longer, and we have to say which columns we want to pivot longer, right? So there's an argument called calls. I want to pivot longer only the yield ones. So there are maybe a few different ways we can specify that. One of them, because they're consecutive, like all the yield ones are side by side, we can just say starting at yield 17 pound per acre, give it a colon, and then end on yield 20 pound per acre, and then it's going to take all 3 columns because that colon gives us a range. So if we run this, that's exactly what happens, right? So it takes all those values and put it below each other. So now we have 3 times as many data rows as we did initially. Because of that, because we pivoted 3 columns. And then for us to know which column heading that value relates to, it just adds another column here called name. And the values of that are the previous headings that we had before. Perfect. Okay, so let's feed this right into a ggplot. So ggplot, I want to call the AES function to specify the x-axis variable. I want to say x equals value because I want those values to be on the x-axis. And because I want to use the geom density does not require a y-axis, so we're not going to give it a y-axis. Because it will calculate the y-axis for us. It's going to be the density of that distribution. Well, I guess, yeah, I can just stop here, add a plus, and then we're going to call geom density. If I run this is so basically the distribution of yield for all 3 years combined, right? That's exactly what we did with pivot longer. So all 3 years combined, this is the distribution of the yield. I do, let me see what So my next step here that I want to show you is if so we have both zones, or well, if you think of it, the yield data that we collected was not in zones, right? It was just the yield for the entire field. So this is the yield for the entire field for 3 years. However, we know at this point what zone they belong to because we made that exercise. So if I wanted to have the fill of the density being colored according to zone. So I just want to show you again, the data coming in is this. So we have a column called zone, right? I can change the fill according to zone. How can we do that? Let me ask Peter. What do you think, Peter? So if I want to color the density that we're seeing, so right now it's a density plot for all the pixels with yield data for 3 years. If I wanted to color them by zone, because we know that those yields are coming from places that have been classified as high or low yielding zones, how can I color or fill them by zone?
So use the color and specify the color.
Okay, where would you do that?
Inside the journals.
Right here?
Yeah.
So you would say color equals. So this is the data that's coming through. Let me show you again. You would say color equals zone.
Eyes, inside the eyes.
Awesome. So like this. Yes, I think that's gonna work. So this changes the color. I mean, I guess that's fine. We can leave the color. Initially, I thought of changing the fill, and I just want to show you here the difference, right? Because so density has both a fill and a color. You can change both if you want, but yeah, we can keep color. So we do see here that once we do that, we can see the yield distribution across 3 years for each one of the zones. So for the high yielding zone, which is the red here, we see that it has a slightly larger mean, but has also this this bump here that has a lot of yield data points here as well, and it has a longer tail. And the blue one, which is the low yielding zone, has an overall lower mean, and it has a shorter tail. So we do see that yield across 3 years is actually higher for zone high, which, I mean, I guess we were expecting that since we had already validated them, but this is just a way of seeing that.
So, I was having an issue with my computer, like, so for me, when I check the zone, the one that you indicate they are low, for me, they are higher, so I was trying to figure out if I did something.
Oh, so the zones here are flipped for you?
Yeah.
Yeah, so this is probably coming from the previous exercise. So when we were on the other project. Let me just launch that. And I guess, it's a good opportunity to show you one of the benefits of using projects, right? I'm just completely changed to the other project and I'm not interfering with my current one. But we did, so that is something that we determined here when we were exporting. So we changed the zone according to the clusters, right? And if you recall, this could be different on your side than what it was on mine. So what I would recommend you to do, and you don't have to do that now, we can do that later. So you don't lose track of the class. But afterwards, you're gonna have to basically re-export this, meaning that you're gonna have to rerun basically everything up until this point. And at that point, do look at these plots and make sure that which zone is high stable, which zone is low stable, because that would play a role here, right? Even if I rerun on my side, it may get flipped again because of that k-means random first step. So every time you rerun this script, you have to, I guess, readjust this step here. This is where you would fix that. And I guess for now, and if anyone else is also having that issue of your zone, your high and low not matching mine here, they should match at this point, because at this point we have already taken that interpretation of 1 or 2 being high or low. If they're not matching on your side, you have to go and fix that on the previous project, but don't worry about that right now, because you can still follow through what we're doing today and still be able to do it all. But of course, you know, you're gonna have to fix it at some point. All right, so I just wanted to show you this so we have some understanding of that distribution of yield and how that's changing. And we're gonna come back to this plot in a moment here to talk about the 90th quantile as well. For the time being, just go to the next chunk. Let's start doing all of those calculations. So we're going to start with the object called zone yield, which is the one above that we merged with all the yield and also zone information. That's our object. Going to give it a pipe. And so before we define the yield potential, we do have to do the same pivot longer as we did on the plotting, because we also need here to have that one column with all the yield values. If you want to just come above, copy that pivot longer and just paste it below, you can do that. If you want to type it out again, you can also do that. But we have to have this pivot longer in place, right? So I just want to run this. So I remove the pipe at the end so I can run it and print VRN. So you see what that looks like. So it has the like 12,000 rows. It has the zone, the geometry. It has a column called name that now contains the previous headings of the EO 17, 19, and 20. And it has a column called value, which now has all the values, right? So now, if I want to calculate the 90th quantile of this value column here on this data set that I'm looking at, I'm going to add a pipe and I'm going to wait for a second here and ask someone, how would you do that? So the task that I'm after is calculating the 90th quantile of the yield distribution for each one of these zones. Amrinder, what do you think? What will be the immediate next step in coding here to do that?
Just multiply by 0.9.
Multiply by 0.9?
Yep.
Not necessarily, right? I mean, we're not going to be multiple. So we're getting the 90th quantile, which doesn't mean that's the 90% of something, right? It is the in position is the 90th.
No.
So let me repeat that again, and maybe someone else can help Amrinder. I want to extract the 90th quantile of the yield distribution for each of the zones. What is the next immediate step in this coding?
Group by first,
Yeah, group by what?
group by zone.
Group by zone. Yes, that's exactly it. That's the immediate next step, right? Because I'm telling you, I want something by zone. So you should be thinking group by. Okay, so I'm going to add a pipe, hit return. What is now the next step? Okay, so we need that quantile function. But if I just write quantile here, it's not going to really work. Yeah. So I have here using summarize. I'm going to do summarize. But we could also use mutate, depending if we wanted to keep the number of rows or decrease them. I want to use summarize. So we're going to say, I want to call this column here yield potential. And then here is where we actually call that quantile function, right? So we say quantile, and then we need to give it the column that we want to extract the quantile from. That column is called value, right? This is what it is in the current data set if we were to run until that pipe. So we want to say value, and then to extract the 90th quantile, we just say 0.9. So if I do run this, and then I print it below, I have each one of the zones. I have yield potential as being like 2,028 pounds of lint per acre and 1,600 pounds of lint per acre for the high and low yield zone. Even though this is a low yield zone, it's still a pretty high potential if you would think about it. But I guess, you know, we don't have to worry about that right now. It's more about the concept of coming up with these numbers. Okay, so what I want to do next is just, so we have this object called VRN that has these columns at this point. I do want to come back here on this plot and add one extra geom that we can do now, we weren't able to do before, which is I want to add vertical lines where those quantiles are based on the zones, just so we can visually see on this distribution, where is that yield potential. So if you come here, you add a plus, let's use geom underscore v line for vertical line. It has this argument called x intercept. So is on where on x you want a vertical line. I want that in two different places that are the two different yield potentials, and that information is in the object called VRN. And then we use the $sign and we say yield potential. So if I just run this by itself, it returns me those two values, right? So if I give that here as x-intercept, it actually plots them as a vertical line. And I also want to show you something that we may have done in the past, I never pointed out. What is the difference if I specify color equals zone on the AES inside geom density, or if I specify color equals zone on the ggplot AES? The difference is that if I specify color equals zone on the top level, so at the ggplot level, that applies to every geom that comes after, if I do at the main level. If I specify within a given geom, it only applies to that geom. So if we say color equals zone at the ggplot level, we didn't even have to say AES color equals zone and the geom density. And that color equals zone at the ggplot level actually trickles down to both geom density and geom v-line. Well, it didn't. Maybe because we have color. Let me try fill. Still didn't. So never mind. But that's what it should have been. So that's, yeah. I'm not sure why. Maybe it's because it's not coming from the same data set, perhaps. But anyways, we can just have here and just, we know that the first vertical line is the 90th quantile of the low yield zone, which is about 1,600. And then the second vertical line is the 90th quantile of the high yield zone distribution, which is just above 2,000 pounds of lint per acre. So that's kind of like our, if we were to get the median or the mean, those values would be lower, right? Which I guess are not the best representation of potential. Okay. So what I want you to do, and I'm gonna ask for some help from you here. So we just come back to where we were. I want to, make sure you run that and make sure you print below here this yield potential. This yield potential is what you would go to UGA Vertex and enter that value there and get a rate out of it, right? So I want to ask for you to do this on your side, and I will ask for some people to help me here. So if you go on UGA Vertex and you change that yield goal to match each one of these categories, and if you just take note of that, it can be below here, the chunk, it can be anywhere. But if you just take note of what that number is, I want to ask a few people here. Tyner, what was the nitrogen rate for the high yield zone with the yield potential of 2,028 pounds of lint per acre?
Still working on it.
What's that?
I'm still working on it.
Oh, okay. Well, has someone else gotten to this part? Yes, Bo.
I think 135.
So let me, bring that here. Yep, I also got 135. So for a yield goal of 2028 pounds per acre, and given my selections, right, with coastal plain as soil, previous crop, cotton, irrigated, it would have been recommending 135 pounds of nitrogen per acre. Yep. What about someone else can help me for the low yield zone? Sandesh, were you able to get there? Well, I'm gonna do here on my side, that would be 115, right? So we're changing a little bit the rate here, not a whole lot, and that's because our yield potentials are not like very, very different, but they're still different a little bit, right? So we're ranging from 115 to 135 pounds of nitrogen per acre, depending on which zone we're looking at. Mhm.
If we, don't check that irrigated box, then we can simple that.
So the irrigated here, I think it only has an effect if you were going with a default yield potential, right? Because if you click on irrigated, it's just changing this.
Yeah.
However, we are providing our own here, our own yield potential. So I don't think that by providing our own yield potential, I don't think that this would change. Yeah, that's a good question. Okay. So we just talked about that. And I guess before we finish here, I just want to show you something. So one way to get those rates is, yes, going to UGA for tax and import, entering the right data and using the yield potential that we calculated here, there, and then bring that value in R. I want to show you a little bit more automated way of doing that. So if you come here after this comment, we can also calculate those. You come here, let's just start a mutate. Oh, let me make sure make sure you add a pipe at this after the summarize, so it connects with the mutate. It's just ignoring all these comments, right? Because they have the hashtag. So this mutate here, I want to create a column that I want to name total and rate underscore pounds per acre. And what I want to do here is if we went to the guide and we look at that table and we saw like yield goal and action rate, and if you just did a regression within those points, you would be able to come up with the actual model behind the scenes that is being able to create the rates both at that table, but also at UG Vertex, which is basically just a linear regression with the slope and intercept, where the intercept is 15. So 15 plus, and then yield potential. So we have a column called yield potential, right? So I'm just calling that column and multiplying that by 0.06. So this is just a linear regression, and is the formula behind UGA Vertex for nitrogen and cotton. So I'm just bringing that formula into R instead of having to rely on UG Vertex to make things a little bit more automated. So if you were to run this, and then I want to print VRN below so we see the results. These are the rates that we get with this formula. So a little bit different, but I think it's close enough for us to call it good. So 137, if we round, pounds of nitrogen per acre for the high zone, and 114 if we round for the low zone. So I just wanted to show you that. Okay, we can stop here. Make sure you save your script. Next class, we will finish this. So we're going to adjust this rate by 25%, calculate the pre-planned rate, and then just finish the exercise. I guess that's all that I have for today. If you had any issues coding or if you have any questions, let me know. Your attendance was already done through the quiz, so I'll see you on Friday.